My name is Roman Melnick. I'm the Manager of Marketing Operations from Transcat, and I'll be your moderator today. Joining us on the call is Howard Zion, Transcat's Director of Service Application Engineering. Howard has a BS in Engineering Technology and an MS in Industrial Engineering and Management Systems from the University of Central Florida. Howard's collected a wealth of knowledge in many disciplines during the span of 32 years in metrology and has been employed with the United States Air Force, Strategic Air Command Female, Lockheed Martin, Electronic and Missile Systems Calibration Labs, NASA and Kennedy Space Center, the Standards and Calibration Labs, Philips Electronics, Metrology and Test Engineering, and then Transcat. Today we'll spend the first time of our presentation and then we'll be answering your questions. At any time during the presentation, you can send your questions through the question box right in your webinar controls. If we happen to run out of time before getting to all the questions, we'll follow up offline to the email or phone number that you provided at registration. I also want to mention that this webinar is being recorded and will be available for you on YouTube. Just search for Transcat Video, all one word. We'll also send you an email with links to the materials once they are posted in the next day or so. Please feel free to share these with your colleagues. At this time, I'm going to turn the presentation over to Howard.
Thank you, Roman. Good afternoon, everyone. Today I'm going to talk to you about intolerance non-conformance investigations. And the learning objectives are to be familiar with the concept of out-of-tolerance measurement risk, a less familiar concept of intolerance measurement risk, the purpose of guard banding, and then comparing this to your organization's current definitions, and if this helps you to help better define those, or if they're not defined, to create those for your definitions. So what we're going to do today is use some examples where you can see why 4-to-1 ratios are important, and it steps through the logical sequence from 1-to-1 through to 4-to-1 scenarios. I created this presentation because of what we see with our consulting with a number of engineers in different companies who have not been exposed to instrumentation, don't really understand the concept of ratios or calibration, really the details of what calibration is for and how it's really there to protect their measurements in the processes for their products that they manufacture. And we see a lot of questions that are coming from different industries. A lot of our consulting is in the medical device or pharmaceutical industries, but this applies to any industry where measurements are being made on product. So we're going to get into those concepts and then how to apply those concepts to controlling measurement processes in order to reduce the whole product false accept or reject situations based on measurements with instrumentation. So from a measurement quality assurance perspective, trying to make sure that measurements are good and you don't have false accept, the traceability of the measurement is important. But it doesn't mean anything if the industrial process doesn't maintain a good measurement quality assurance program. There are many steps in doing that, aside from calibration of the instrumentation. Measurement quality assurance is critical to industrial manufacturing processes because it helps to keep product costs down, helps to maintain safety for employees and product consumers, keeps product lead times from being delayed, and in the end, the whole purpose of the traceability chain from the National Metrology Institutes through to the measurements on the product is there to make sure that those measurements are protected. And if the last step in the traceability chain on the product drops that ball, then it was all for naught. So an important part of using cal data is to control the product decisions. Instrumentation quantifies whether the product is good or bad for different parameters of the product. And if that instrumentation is leading you astray without you knowing it, well, that's really the purpose of the calibration process. But that can also happen because of other reasons. And that creates what's called a false accept or a false reject situation. So in a previous presentation, I came up with 10 different ways that this risk can creep into decisions about product. Pass or fail, or any testing for that matter. So product acceptance is making the right decision about the product based on quantification using instrumentation. That's number 2. Number 3 is suitability for the intended purpose, and that means you're using the right tool for the job, the right instrument to make the measurement. And instrument application is using it correctly. Is there training that needs to be involved? Are there factors that need to be accounted for? Is there functions that have to have math corrections? There's a number of things depending on instrumentation, and instrumentation is so varied that it really gets specific to the type of instrumentation you're using. So it's important to use it correctly. Beginning and end of period reliability of the calibration data showing that the instrument indeed maintained its performance specs, or if it was customer driven for the tolerances on the instrumentation to make sure it met those specs. So end of period reliability is really the part of calibration that's the most critical to say, how did this instrument end up at the end of the calibration, and could there have been any differences in the decisions made on product if that end of period calibration indicated it was out of tolerance. That's usually how people think of it. Take a look at the calibration at the end of the period of its cal interval and see if there were any impact at all, if it was out of tolerance, on the product. But this concept takes it a step further and says, wait a minute, there could be an intolerance situation that causes product false accept. And that's what we're going to show in some of the examples. And then beginning of period reliability says, okay, so at the end of the period, you check the instrument, you see whether it's in or out of tolerance. If it's out of tolerance, or if it's close to the tolerance, you make adjustments to get it back to where it needs to be, closer to nominal. And that becomes now the beginning of period reliability going forward for the next calendar. The calibration process itself, if the calibrations aren't being performed correctly, or if they're using the wrong specs, wrong methodology, there could be a number of reasons why you think you have a good calibration result, and when you dig into it, maybe it wasn't done correctly. It does happen, more than it should, so buyer beware when you're sending out instruments for calibration to any external supplier and even for internal labs. And then once you get the data back from the calibration, typically, like I said, if it's out of tolerance, you're going to do a non-conformance review to see if there was an impact from the calibration data to the product decisions. And again, that can also be impacted for intolerance results if you have low ratios. How well that non-conformance review is done for out of tolerance or intolerance situations is critical as well. If it's just brushed off and passed through and didn't really have the right logic or justification, then again, the traceability chain all the way to the product, for this end result of showing an out of tolerance instrument, for example, wasn't carried through to the measurements on the product correctly, and in that case, the whole process was for naught. So the accuracy of the non-conformance reviews is very critical as well. You may have attended one of our other webinars that Phil Mastretta gave on out of tolerance processes and how to perform out of tolerance evaluations. Very popular webinar, and we've done some seminars with select clients as well. It shows the step-by-step process and how to do that correctly. Risk mitigation is any negative result that may have impacted the product itself. So after the non-conformance review was done correctly, you see that there could have been an impact to the product. That may require rework, scrapping of the product, or recall if it's already been released. So that step also is the final step in making sure that false decisions on product didn't get out to the consumers. So all of these steps are critically important. We're going to take a look at the intolerance situation with low ratios where that can impact decisions about product. And when I say, hey, intolerance to non-conformance investigations to people, they say, you're kidding. I have to worry about an intolerance situation. I'm only looking at my certs to see when it says out of tolerance. Well, unfortunately, that's not the case if you have low ratios. This is something that we call a quality blind spot. If you are not familiar with how these numbers line up from calibrating the instrument to the ratios that are used for the standards calibrating your instrument or for the ratio from your instrument to the product tolerances. If those aren't healthy tolerances, you can have situations that are creating a problem with false accept of the product without you even knowing it. And that's what we call a quality blind spot. And there's a lot of points in these 10 steps that I've identified where quality blind spots occur. So being aware of them is the first step in making sure you get rid of that and improve your quality measurement assurance. So the evaluation of understanding these concepts is a little bit complex. It's not overly complex, but it takes some steps that you walk through the whole process to see how it applies at different ratios, 1-to-1, 2-to-1, 4-to-1. And we'll do that today. An understanding of this particular intolerance quality blind spot also requires knowledge of test accuracy ratios, or TAR, the concept of test uncertainty ratios and what the differences are there. And then there are a couple of terms that Transcat has coined when we try to differentiate between calibration of an instrument used in production, when we calibrate the instrument in the lab, versus the use of that instrument to make decisions about product or a process, a manufacturing process. And so we call that a process accuracy ratio when you're looking at the instrument used to measure process tolerances, or a process uncertainty ratio, so PAR and PUR. So we're going to use an example in medical device manufacturing that everyone can relate to. And we'll look at product measurements over a period of 1 year. It's a low volume manufacturing operation, so we're not inundated with hundreds or thousands of the product to evaluate. As we go through the measurements, we'll logically step through the reasoning behind a 1-to-1 ratio, 2-to-1, and why we go to 4-to-1 or better. So in this example, we're looking at a heart-lung bypass machine, what's known as perfusion equipment, where in an open heart surgical situation, you're using the machine to keep the patient alive while the heart is stopped and is being operated on. The patient's body temperature is maintained at a hypothermic state between 28 and 32 degrees Celsius. Measuring influent and effluent temperatures in this process with the product. And the process tolerance for the effluent flow is 30 degrees C within 2 degrees. Again, 28 to 32. 30 products manufactured over a period of 12 months, 30 of these heart-lung bypass machines in a 12-month period, and we plot their results here on the temperature values. So as you can see on the left end of the chart, we had the first measurement on the product, which happened to be right at 30 degrees Celsius. You can see the other values here. We had a value here at the low end below the limit of 28 degrees. And so in that case, the measurement was taken, and then an adjustment would have been made to bring it back to where it needed to be, back to 30. Same thing with this one that was above the tolerance limit of 32. And so the measurements occurred as found here, like this, on the product. One point to make here is that if during these types of surgeries, the temperature of the patient is not maintained within that tolerance limit, you could put them into a situation where they either have brain damage or it could kill the patient. So it's critical to make sure that this is maintained. And I'm sure there's somewhat of a buffer there, but the design of the product is such that it's 30 plus or minus 2 on the effluent temperature, and that's what we're measuring for this example. All right, so graphing a single point at 30 degrees. We have the nominal at 30. We've got to determine what type of inspection, measuring, or test equipment is suitable for that measurement on the product. Is it an instrument with an equal accuracy to the process limits? That would be a 1-to-1 ratio, or what we would call a process accuracy ratio. So let's look at that scenario to see if that is something that's suitable or is not suitable. That will end up not being good because the instrument itself can drift the full amount of the tolerance allowed for the process. So for the instrument value that was calibrated on May 12, 2014 from that original chart, it was the first one on the left. The instrument was used to measure the effluent temperature on the same day that it was calibrated, that the instrument was calibrated. And so it's right at 30 degrees C. And you would call that process measurement good. If I calibrated that instrument that day and I took it out on the floor and made a product measurement, unless I dropped it or did something to cause some shift on the instrument, it should be right at 30. It should, if that product measures 30 degrees, it should be right at 30, based on the calibration that was just performed. Now, on the last day of the instrument's calibration cycle, just before it's recalibrated, the instrument's used to measure the effluent temperature on the product on May 11, 2015. That temperature was right at 30 as well on that product. So we would assume that that process measurement is good as well. It's right at 30. That's what the instrument is indicating to us. If we don't make any adjustments to the product, we put it on its way out the door. Now, on the 12th of May, 2015, the instrument is recalibrated. That's used to make the measurements on the product. We find that it's at its upper limit. Traditionally, we call this an intolerance reading. Not looking at measurement uncertainties or anything to complicate this at this point, just keeping it simple and understanding simple ratios. We're looking at the traditional viewpoint of saying that this is intolerance and we would not report it to the customer as out of tolerance. And so when the customer looks at the calibration certificate on this instrument, they see that the statement of compliance shows as received intolerance. No other steps are taken because they're used to seeing if it's out of tolerance, they'll take a step. If it's intolerance, they don't. Pretty common. So this drift from where it was calibrated a year ago till now occurred over the calibration interval. And then we found it to be intolerance, but at the upper limit, adjustments are made to bring it back to nominal. So the question is, did that instrument drift linearly over that 1-year cal interval, or did it do it all at once at some point in time? And you won't really know that unless you have control points or people paying attention. If they dropped a gauge or an instrument, making sure they're diligent in sending it in for calibration to have it checked out. There's other ways to have midpoint checks, cross checks to see if the instrument has been drifting more than it's allowed, to prevent out of tolerance situations, or to prevent things like this at the upper limit. So there's a number of things that can be put into place that'll guard against that, but let's not go there quite yet. The question is, we see that this was at the upper limit. We call it intolerance. Don't know if it moved all at once. How does it impact measurements on the process? That's the last time the instrument was calibrated. So let's look back over time and see what that is. The error in the instrument is the reading on the instrument, subtract the standards value, and so we see that there's a +2 degree error. To correct that, on readings that were taken over time, we have to subtract 2 degrees to get it back to where it should have been, had it not drifted at all. So on the out of tolerance NCR evaluation, it would be assumed that the shift occurred immediately if we had an out of tolerance situation. Following the last cal, because it's the only supporting evidence that shows the last known good condition of its temperature values. And this is where I talked about having midpoint checks or regular checks in between with a cross-check standard that helps you identify when one of your instruments used on product is drifting. If it's drifting too much, then you would go ahead and send it in for cal prematurely to make sure there's no problem with measurement on product. So that's one way to guard against it. So returning to the product measurement made on the 12th, the very first one used after its cal interval, or at calibration of the last calibration. This was the one on the left end of the graph. It was shown to be at 30 degrees C right after the instrument was calibrated. But if we don't have any supporting evidence that proved that it wasn't dropped from the time it was cal to the time it was used, Again, the conservative measure is to say, at the end of period, at the end of the cal interval, we saw this was intolerance, but at the very upper limit, we have to assume that that was the case until the last known condition. Anything used, anything it was used for to measure product after that very point in time would have to be assumed to be off by that much. I know that sounds crazy, and it probably isn't the case, but you have to make that assumption unless you can prove otherwise. So now is the process measurement good? We thought it was at 30. We do the -2 degrees C correction. We would have been at 28 degrees C on that measurement, on that product. So process measurement is still good according to the tolerance limits we have on the product, but it's right at its limit. And again, probably not a good way to turn out product. Now the same applies to the process ratings at the end of the cal cycle as well. What if one process rating had shown the product was at its lower limit already? Again, this is why you wouldn't want to turn out a product at the lower or upper limit. So in this case, had one of those measurements been at 28 degrees C, and then we found out that it was actually reading 32 when it should have read 30 at the end of its cal cycle, making that correction now would have pushed that measurement from the product to have been out of tolerance, and that would be a false accept situation. And the intolerance calibration statement on the cal report for that instrument, temperature instrument, would not have flagged this at-risk situation. Again, you're looking at the cal cert, you're not putting all the pieces together because there's nothing to help you do that. You just have to be aware of situations like this when you're at a one-to-one scenario. So that process measurement was actually bad. All right, so now if we take a look again at those initial readings that we captured on the product over the year, and we make that correction on the instrument based on its end of period calibration, those values actually shifted down 2 degrees Celsius. And now we have a situation where we have all these in red that are at risk. The one that was above 32 degrees C was then falsely rejected or falsely adjusted. There was labor spent, so there's the cost, right? Falsely adjusted, and the value that was at the below the lower limit of 28 is correctly rejected. It's just further out than we had thought. And everything in between up to the tolerance limit now with the corrections involved show that those were false accepts, quite a few of those false accepts. And so at the end of period reliability, when the instrument's recalibrated, that's when we find the results of what truly the measurements were on product. Again, taking a conservative viewpoint, correcting all the way back to the last known good point, the last cross-check, the last mid-cycle check, or if none of those existed, all the way back to the last calibration date. And that's what makes out-of-tolerance non-conformance evaluations so costly. If you're not doing any of those midpoint checks to show justification for why you don't have to go all the way back to the full cal cycle, then you've got to evaluate all product all the way back. Also a good reason why not to take things out to 5, 10 years or more on calibration cycles, because you're increasing your liability and cost to handle out-of-tolerance evaluations correctly, thoroughly. So in a one-to-one situation, it's too risky. You've got too much variance there, too much ability for the instrument to move within its allowable range and still cause an impact to the measurements on the product over the cal interval of that instrument. All right, so what if we went to a 2-to-1 ratio instead? Now, if the instrument drifts to its tolerance limit, the process readings would only be off by half of the process tolerance. Okay, so skipping through the whole concept that we've just gone through and seeing what the adjusted temperatures would be based on an instrument being plus or minus 1 degree instead of plus or minus 2, which is the process tolerance. We now would have 4 scenarios that we'd have to consider of instruments that were shifted enough to be concerned about. Again, that falsely rejected one at the top, still exists because had we had the correct measurement from the temperature instrument, had it not drifted, we would have not made the adjustment on that instrument. The low one, which was below 28, still correctly rejected, but further out than we had originally thought. And then there's now 2 that were falsely accepted and now are out of tolerance, based on that history record of the calibration of the instrument. So 2-to-1 ratio still is too risky. We can do better. This is where we go to 4-to-1 to take a look at what would happen there. Now, if the instrument drifts to within its tolerance, not out of tolerance, we could be as far off as 1/4 of the process tolerance. So it's minimizing that risk. And in this situation, we would have no falsely accepted situations in this particular case. We'd still have 1 falsely rejected and 1 correctly rejected, but further out. Not as much of an impact. Now, in all of these scenarios, if the temperature instrument was calibrated and found to be out of tolerance, that would have normally triggered an out of tolerance evaluation, and you would have gone through this process anyway. The point here is to find the blind spots, the quality blind spots, where you don't see an out of tolerance on the calibration of the instrument, therefore you don't do an evaluation. You had a lower ratio, process accuracy ratio of the instrument to the product tolerances, and you should have been aware enough to know to go back and evaluate that. So I'm sure you're still saying, I don't want to have to do that. How do I prevent from doing that altogether? So the 4-to-1 ratio is much better. How far can we take this? 10-to-1, 100-to-1, how far can we go? A lot of it has to do with limits of technology of instrumentation, what you're trying to do with your product as well, or the measurement process in manufacturing, how tight you're making those tolerances, how loose those can be. Eventually it becomes cost prohibitive to go too far with this concept, if you can, if there's no limit of technology. So there's boundaries that keep you from going too far with this. 4-to-1 ratio generally produces about a 2% consumer risk. We're not going to get into the details of how that is calculated. There are many, many white papers on those details. But the point is we're reducing that consumer risk to get it to a reasonable level. We go to 4-to-1. Pretty widely accepted and practiced. Some measurement processes require that you go further than that, 6-to-1, 8-to-1, 10-to-1. Depends on the measurement. Again, there's a lot of parameters, a lot of different instrumentation out there. And it also depends on the criticality of the product. If you have a very critical product, 2% consumer risk may still be too much. So understanding all of these concepts and applying it to what you're trying to do, and that's really what it has to come back to. What are you trying to do in the manufacturing process? What are you trying to measure? And what are you calling a suitable instrument for that measurement? So the lessons learned here are that even intolerance results can impact your process measurements, depending on the ratio, depending on what's being used for. All calibration data really must be reviewed against process measurements to understand the impact that it's causing to product. But impact studies are expensive, and it consumes valuable resources, and you want to try to avoid that altogether. And if parts or the product itself has been released or shipped, that can be very costly as well. It could require product recall. If it's not released, it could require rework, whether it's adjustment or partial remanufacturing or scrapping. And the good news is that risk can be reduced using what's called the guard banding process. So what is guard band? You determine your tolerance limits for the process. However you normally go through that process to figure out what those limits need to be. And then you back off from those tolerances the suitable instrument that you choose for the job, for the measurement. You take its tolerances and back those off of those process tolerances to give you upper and lower acceptance limits to allow for enough room for the drift in the instrument without it impacting measurements on the product. Now, if the instrument cal reveals a drift up to the maximum tolerance, there's no need to perform an intolerance nonconformance review. Now you can truly wait when you do this guard banding until it is out of tolerance and you receive a statement of compliance on the cert that says out of tolerance. You can't have your cake and eat it too. You can't have a situation where you don't guard band like this and expect to only rely on out of tolerance situations before you do an evaluation. If you're not doing this guard banding to protect yourself, still have a small percentage, 2% consumer risk in a 4-to-1 ratio, 2% risk that you could have intolerance, instrumentation, calibration results, and impact the product measurements for false acceptance. So you need to guard band, and then you can rely on the out of tolerance solely as an indicator of time to do a nonconformance review. Here, in this case, when you do guard band, your process measurements are now protected. And now, in that situation, if the instrument is out of tolerance beyond its limits, then a normal out of tolerance nonconformance review would be performed. So here's a look at the impact of the as-produced readings if you were to guard band. These readings in the guard band region would not be allowed to be released for the product measurements. Instead, those would be flagged as needing to be adjusted within the acceptance limits. And that's, once you guard band, you put a guard banding process in place, that's how you're protecting the measurements from having instrument drift with intolerance that affects those measurements. So in summary, implementing a good measurement assurance program all the way down to product measurements is very critical. Understanding and exercising good suitability selection. We have consulting and white papers on that topic. Guard band the process tolerance limits to reduce your chance of having an intolerance nonconformance situation that causes false acceptance of product. Understand both the process and the calibration of the instrument to ensure that the intent of preserving good measurements on the product is not lost. And what that means is, what are you trying to do with the measurements of using the instrument on the product? Make sure your calibration is covering all of those functions and ranges that you're trying to make measurements with, that there are tolerances assigned either from the OEM who makes the instrument you're using, or if that's not sufficient for your process, that you're defining a custom calibration for that so that you're covering what you need to cover in the measurements of the product. When you perform a nonconformance evaluation, once you've guard banded the process and you have an out of tolerance situation, make sure it's thorough. Make sure you're taking all the steps to find the truth of whether or not product was impacted. And if you need help, if you're in over your head, call us. We do consulting, and we have a number of white papers that maybe help you with this concept as well. But it's critical to having good product that's safe and keeping your costs down. So in the end, running your business is not just about meeting standards or policies. It's about making sure your product's safe and reliable and superior to other products on the market. Measurement quality assurance covers a number of different topics that can cause risk in your process. Make sure you're doing all of those, because if you're not, risk is going to creep in one way or another. Guard banding processes is a key part of guaranteeing good measurements results, good quality assurance. Too often, one or more of those 10 categories is not implemented, and that causes reliability of your measurements to lose value, become ineffective, and possibly put out bad product without knowing it. Quality blind spots, that's what you're trying to avoid. If you're going to put the effort and money into only some parts of the program, of those 10 steps or whatever else is involved with your quality program, why not do it for all of them? Because one of them could cause you to have bad product, and you don't want that. Cause you more money, more cost, safety, bad perception from the public. So make your quality assurance program robust. And that is the end of the presentation. I'll turn it over to Roman for questions.
Okay, thank you, Howard. So that concludes the presentation portion of our webinar. Now we're going to move into the questions and answers. Just a reminder, if you would like to ask a question, please send it through the question box in the webinar controls. We do have a couple of questions that have come in. The first one is, you mentioned suitability of instruments. How do we determine if we have the correct instrument?
So there's, I believe, a white paper on our website that you should look at. There are a number of steps that you want to look at, including comparing the instrument's functions, parameters, the ranges, the readings, the tolerances of the instrument from what the manufacturer states, and comparing all of that against what you're trying to do with the instrument in the process of making measurements and those process tolerances. It shows you step by step how to go through those comparisons. And if you have further questions on that, feel free to call us.
Okay. The next
that paper is called Suitability of Instrumentation.
Okay, and all of our white papers and previous webinars are located on our website at transcat.com under the Resources tab. The next question is, do you bring the specs to the same confidence level before making this comparison?
Let me think about that in a minute. So the specifications that we're talking about, there's two sets of specs. One is the process tolerance itself, what's being measured with the instrument, and the other is the instrument's tolerances, which are stated from the manufacturer, and that can be, depending on the instrument, can be a straight statement of accuracy. It can have combination of accuracy, linearity, repeatability, hysteresis. It can have different uncertainties based on different calibration cycles, 90-day, 1 year, 2 year. It can also have specifications from the manufacturer based on confidence levels, which is more of what you see from Agilent and or Fluke instrumentation, but there's a lot of manufacturers out there that have nothing like that in their specs. So that gets into the question of, going from looking at simple accuracy ratios to uncertainty ratios. And when you're going to that level, you want to make sure all of your components in an uncertainty budget, if you're familiar with uncertainty budgets, are at the same confidence level. So you would want to bring those all to the same confidence level at that point. If you're not as advanced and don't understand uncertainty concepts, just start with accuracy ratios and see what you have, whether it's process accuracy ratio of the process tolerances to the instrumentation being used to measure, or test accuracy ratios that are comparing instrumentation to its calibration standard. Start with that, and then you can work your way into the more complex concepts of uncertainty ratios.
Okay, the next question is, what is the normal guard band percentage?
Well, the guard band percentage, it turns out to be whatever the percentage is based on the ratio, right? So what you're looking at is whatever the tolerances are in the process divided by the tolerances of the instrumentation for that measurement. And that ratio comes out to be whatever it is. When you apply the tolerance of the instrument to a guard band situation to reduce the process tolerances to an acceptance tolerance, it's not necessarily a percentage so much as it is making sure that you're covering the range that the instrument could drift over its cal interval before it's considered out of tolerance. Now, in a 4-to-1 situation, that ratio is going to be 25%. In a 3-to-1 accuracy ratio, that's going to be 33% of the tolerance of the process. 2-to-1 situation would be 50%. So that's how the ratios end up coming out and the percentages.
Okay, this is a similar question, so it might be a follow-up, is do you have any guidance on how to determine and develop a guard banding process?
I don't know that we've actually written any papers on that. There are a number of white papers out there through NCSL, Measurement Science Conference, American Society for Quality may have some. But in any case, for guard banding, effectively, like I said, you're guard banding the process tolerances by subtracting the full tolerance of the instrumentation being used. It's just that simple. You get your acceptance tolerances by subtracting the tolerance of the instrument from those process tolerance limits. And that's your new acceptance limits that once it goes beyond that, then you get into a situation where the instrument could have drifted enough to cause a false reject situation. Hopefully that answered the question.
Okay. Next question. Can you cross-check with a similar instrument with a similar accuracy?
All right, so let's talk about that for a minute. It's a very good question. Cross-checks aren't about having the accuracy of a check standard that is good enough to do a calibration on the instrument. Resolution comes into play a little bit there, but really what you're after with a cross-check is taking a measurement at one point in time as a reference point. So it's a relative measure. And then at some other point in time in its cal interval, taking another measurement and seeing if it's drifted. Now, the trick there is having enough resolution to determine whether there's been enough drift that causes concern, right? So that's where the resolution comes into play. But also, making sure you have that base point, reference point, right after the calibration. When you receive it back from calibration, taking a measurement at that point in time as your base point. That's what you're going to use to compare it to see if there's been any drift. And if there's anything that's considerable drift, at that point, stop using it in the process, send it in for cal, make sure it's okay. What you may find out in those situations where you think there's a potential risk can be a number of things. One could be the instrument is fine and the recalibration shows that it's okay, and then you find out maybe there was some operator error, something that caused that erroneous reading. You could find that the instrument was actually at fault. It was drifting for some reason, or you may never know if somebody dropped it or caused it to be out of tolerance prematurely. But at least you'll be catching it before you're using it to put out a product that's no good. So the cross-checks are critical to do, but the point of the cross-checks is to have a base point and a comparison point over the cal interval before it's recalibrated, before the instrument's recalibrated.
Okay. How do you classify a point that falls between the acceptance limit and the limit? In tolerance, out of tolerance, not determined?
So that gets into two different areas of discussion. Let's keep the simple point of view, and that is if you're in the guard band region, which is between the acceptance limit and the process tolerance, where you're trying to guard against having any problems there, at that point you want to call that product measurement at risk, right? Call it at risk, and make an adjustment on the product to get it back out of that risk region before you turn it out, before you release it. So that's the whole point of the guard banding, is to catch those items that could be at risk and keep them from being at risk. The secondary way to do that is looking at risk scenarios and measuring the amount of risk, looking at uncertainties of the measurement, getting into measuring, quantifying risk in the process. That's a lot more complex, really not the topic here. You can get into that, but I think the basis of this whole guard banding concept is to not allow that to be turned out, make an adjustment to get the product back out of that risk situation.
Okay, we have a follow-up question for the cross-check question we just covered. In the case of a one-to-one cross-check, if there's a significant drift, then wouldn't we have to suspect both participating instruments in the cross-check?
Yes, you do. If you have a baseline point, you're doing the same thing. You're comparing the two. Now, the odds of both of them drifting the same or drifting differently, well, they can. I mean, they both have the same tolerance in a one-to-one situation. It's really not meant to be an absolute measurement on accuracy. It's meant to be an identifier of potential risk, and that's all it's for. So in that situation, I had mentioned that you might find that it's operator error. You might find that the instrument itself is bad. If you find that neither is the case, you may find that your check standard's bad, right? That could be another scenario, so it's a good question to bring up. But the point of it is to identify potential risk before it becomes a problem with your product. And even if you had to take the step of finding out that the check standard had a problem, better than putting out bad product. So it saved you in the end. I hope that answered the question.
And it looks like we just have a comment and one of our viewers that said, thanks, it gave me a much clearer way to visualize TAR for my trainees, plus the inherent safety factor in the 4-to-1 ratio.
Thank you. I appreciate the comment. And Roman, you'll be putting this up on the web as well, correct?
Right. So that concludes our time for today. If you do have further questions or want to find out more about our service offerings, products we distribute, or how we can consult with you, please feel free to contact us at the number shown on the screen or visit us at transcat.com. We thank you for joining us today. Again, in the next day or two, we will put out an email where you can both download the slides as well as view the webinar recording. We hope you have a great rest of the week. Thanks for attending.
Thank you for attending.